In this lesson, we'll talk about another of the advanced topics on the GMAT exam, and that's going to be functions and weird symbols. So this problem here on the screen is setting up basic function notation. We can see an f with an x in parentheses and then an operation that is occurring to the right of the equal sign. Now, the way that functions work is they dictate operations performed on the variable. So whatever we plug in for x, we're going to add 1 to it and then divide by the value itself according to this function. So you read this as f of x, and we know that f of x notation is the same as y equals notation in the coordinate plane. Just kind of a tertiary concern that you may see on the test. And nested functions, meaning a function within a function, they have to be processed from the innermost parentheses outward. So you always start in the middle and then work your way out. So let's consider an example here of this function. So what would be the f of 2? So the first thing we have to do is process the function using 2. And that's just going to be 2 plus 1 divided by 2, which produces 1.5 or 3/2. And remember that generally, as you consider arithmetic operations with a decimal or a fraction, usually the fraction is going to be easier, and we're going to end up using that 3/2 next for the next f of x. But again, you can consider it as 1.5 or 3/2, and we end up with 1.5 plus 1, or 2.5, 5/2, divided by 1.5, and that gets us 1.66 repeating, or 5/3 is an improper fraction. So that would be the answer to what is the function of 2. Now, what are the implications of this? First, understand what domain means. And domain is going to be the acceptable inputs that produce real values in the function. So for this function, the domain of it is x cannot equal 0, because if x is equal to 0, then we end up with 1 divided by 0, and we know that dividing by 0 produces a non-real result, a non-real quotient of infinity. So the primary domain constraints that you're going to encounter here with functions are that you cannot divide by 0 and you cannot square root a value that's less than 0. Because if you square root a negative, again, you're going to get an imaginary number, and the GMAT only deals with real quantities that can be expressed on the number line. Now, let's talk about symbols. So GMAT symbols are basically just another way of articulating a function. So these are going to be unique arithmetic or algebraic operations. They are not necessarily defined rules of math. So they're going to be basically follow the instructions kind of questions. You just have to follow whatever the definition of the symbol is and complete the problem following those rules. So, as we just said, follow the format as it's presented. They are similar method to functions, and so there are some strategic implications here as well. First, you have to stay calm. The primary way that the GMAT generates difficulty from these weird symbol problems is going to be just the initial shock and awe, and trying to a degree, overwhelm you with just like, what am I looking at? Remain calm, and it's usually not as complex as it initially seems. Now, the symbol function may or may not be predicated on defined rules of the mathematics, and you can have all sorts of different definitions, all sorts of different applications. You just have to follow whatever the rules are. And that said, you do have to apply things like PEMDAS ordering, the basics around how addition, subtraction definitions might work to the mathematics of the symbol or the function. But you have to make sure that you're following the instructions of the function basically first, and then making sure it does not violate any rules of arithmetic or algebra as we know them to exist. So let's just look at an example of a weird symbol. So we've got this kind of 4-pointed star, and if this 4-pointed star represents a unique digit in the equation 5 star star plus star star equals star 32, what is the value of the star? So first, we stay calm, and we go, okay, this is something weird, granted, but it's probably not as complex as it initially looks. So begin with the known information, and in this case, we know that 500 something, because it's a 5 in the hundreds digit, then 2 subsequent digits, so tens digit, units digit, plus a 2-digit integer is going to equal a 3-digit integer that's ending in 32. That's what we know so far. But we also know that if the 4-pointed star is a unique digit, itself cannot equal 5. So that's the logic that makes us go, okay, the only other possible hundreds digit, if you're adding a 2-digit value, a 2-digit positive value that is, to 500 something, is going to be 6. So that means that the star has to be 6, because you can't add 2 digits, 70, 90 to 500 something, and get a 700 or 800 value. That will require another hundreds digit. So we know now that the star has to be 6, and we could just plug that value in for 6 to confirm that everything follows the construct of the problem. And sure enough, 566 plus 66 is 632, and we see that that one digit represented by the 4-pointed star is constant throughout the little equation. So this is just an extrapolation of all the concepts, but let's just talk briefly to conclude here on the slides about our weird symbol and functions process. So step 1 is just going to be to set up the scratchpad for the problem. You want to carefully read and define the function or symbol as presented to inform either your problem solving or data sufficiency processes. So you're going to basically follow everything that we've done with problem solvings and data sufficiencies through the weird symbol and function process as well. Step 2 is going to be to carefully apply that function or symbol as required by the problem. So very frequently, you'll want to use an example to illustrate the function or symbol if needed. And you'll want to consider what the implications are and how you work through the symbol or the function. And sometimes they'll actually give you an example as well, and you'll want to consider it. You'll then want to consider the logical implications of the function or symbol as defined. And we just did that in that previous example, right? We're like, okay, we've got a 2-digit number added to a 3-digit number. What does that mean? And then step 3 is going to be to consider your best approach for solving. Now, you want to take a technical or logical path to solving if you can, but you're going to frequently want to consider the alternative tactics of plugging in the choices or easy values. And functions and symbols are one of the rarer places where you might even consider plugging in a little bit more as a viable option for data sufficiencies as well. So just know that frequently you'll have to plug in your own values, plug in some answer choices, and again, potentially model what the function or symbol means in the first place as an exemplar in order to work through these questions. So let's head on over to the whiteboard and take a look at a problem solving and data sufficiency example of functions and symbols on the GMAT. So we've got a sample problem solving function question here, and we'll just set up the scratchpad as we always do, A through E, and we're being asked for the value of f of x squared. Now, the way that this is structured is such that if you see an algebraic approach, you probably want to do it immediately. But if you don't immediately see an algebraic approach to this problem, you'll want to consider our alternative tactics. And we know that if we've got variables throughout the problem and in the choices, that these are all going to be plugging in values or modeling clues. So with that in mind, let's consider that as our primary tactic. So we know that we've got 2s and 4s throughout our answer choices. So that means we probably don't want to model using 2 or 4. We'll pick our next easy number and just go, well, let's say if x is equal to 3. So if x is equal to 3, then we know that x squared would be equal to 9. And so if x squared is equal to 9, that means that our function would be 1 minus 9 squared, which would be equal to negative 80. Because, of course, 1 minus 81 is going to be negative 80. So we want to look to our answer choices and find something that matches negative 80. So x to the 4th, well, that's going to be 3 squared. So choice A is 1 minus 81, and sure enough, that is equal to our 80, so that seems good. But remember, you have to test all 5 choices to confirm there are no duplicative answers that match our model in our scenario. So then the second option, we've got 1 plus x squared, which is just 3 squared, which is 9, and that, of course, is 10, and that's not going to match our negative 80 we were seeking. Then with choice C, we've got 1 plus 2x, which is going to be 6, plus x squared, which is going to be 9, and that's just 16, so that's definitely not negative 80. And at this point, we probably can kind of see that it's not ever going to get above or get down to negative 80 because we've got to subtract our value, and we're not going to offset that plus x to the fourth. So if we did 1 minus 6 again, but plus what we know is 81, well, that's way over 0. So that 2 is going to be out. And of course, 1 minus 2x squared, well, that's going to be 1 minus 18, but still plus 81, which is going to go well over that 0 again, thus leaving us with our initial match of choice A. Now, the alternative algebra, we could, again, if you see it, just plug in x squared. So we'd have 1 minus x squared squared, which is going to be equal to 1 minus x to the fourth, and that, of course, matches our expression directly as well. So consider both approaches, plugging in values if you don't see the immediate algebra, or potentially doing the algebra if you do see it, because again, remember, technical approach is probably fastest if you can do it. Now then we will scroll on down and we'll take a look at one more example here. And we've got a weird symbol. So data sufficiency, going to still, as always, set up with what we know. And we start with, for any two unique positive integers a and b. So there's a lot to unpack here, believe it or not. First, we know that a is greater than 0. We know that b is greater than 0 because they are positives. We know that there are no fractions because it says they are integers, and we know that they are unique, so that means that a cannot equal b. So then we find out that this a with a rectangle of b is equal to the greatest common factor of a and b. So remember, we said that oftentimes you'll want to consider an exemplar to see what's happening. So let's just say, well, if a were equal to, oh, I don't know, let's make a equal to 12 and we'll make b equal to 18. Because then that means that 12 with this rectangle 18, well, we just have to know the greatest common factor of 12 and 18. And we know that 12 doesn't go into 18, and 12 is the biggest factor, or 12 is the biggest factor of 12, so 12 won't work. But then the next biggest factor of 12 is 6, and 6 does go into 18. So we know that if we had that 12 rectangle 18, we'd get 6. So there's a whole lot of information here to start. We also know that ultimately we're looking for x with that rectangle y as our question. So we'll box that off. And what we need is going to be some method of determining the factors of x and y. And when we have these factors and the methods of determining them, we know it's probably not going to be all that algebraic because we're talking about something that isn't really easily articulated in an algebraic fashion. So condition 1 says that x is equal to 16. Well, okay, so we're looking at the greatest common factor of 16, box that y. Well, if y equals 16, then we know the answer is 16. But let's say y was equal instead to 20. Well, then the greatest common factor of 16 and 20 is just going to be 4. So we've got two different outcomes. That's not going to be sufficient. B, C, or E. Now, condition 2, we have y is equal to 17. So that means we've got x and our rectangle to 17. Well, that means that x no matter what x is, we know it cannot be 17. And we're saying x is the greatest common factor of y here. So there's only two factors of 17. It's either going to be 1 or 17, and they can't be the same. So x must be, or the x rectangle rather, must be 1 because there's no other factors for 17. And this by itself is sufficient, even though we only get one of the two values. So having looked at one of these higher end difficulty concepts of functions and weird symbols, go ahead and attempt some practice problems similar to these to get familiar with what is certainly one of the most daunting aspects of the quantitative section.